Benchmark. Let's take a look at another micro benchmark. Here, I'm testing how long it takes for me to append to a list of words. And I'm going to just append the words case folded. They're already lowercase, so this case fold operation really shouldn't do anything that interesting. And here you can see it takes about 59 microseconds. If I compare that to my comprehension syntax, here you can see instead of 59 microseconds, it's 52 microseconds. Now this is on about 1,000 elements, which is fairly realistic. I often have Python lists of 1,000 elements that I put into comprehension syntax. And it's definitely the case that when I look at this, and we should really mark most of these as Python 3, I get an improvement with the comprehension syntax, but I again feel like that's not the point of the comprehension syntax, because you can see in some versions of Python, this comprehension syntax here took 73 microseconds in Python 3.10. Let's see what that loop took in Python 3.10. And if it's the case that the loop in Python 3.10 happened to be slower than the comprehension, is that really something that's going to guide me to rewriting my code? Well, thankfully, it's not slower. Python 3.10 and 3.9 seem to have a performance degradation. And so we're lucky that it doesn't give us that adverse advice. But still, I don't think this is the direction of advice that we should be taking in the first place. Because unless we can structurally say this must necessarily always be faster, it could very well be the case that in one of these versions of Python, somebody added an optimization somewhere deep in the interpreter to make one of these two faster, but they didn't add it to the other place. And as a consequence of only adding in one of the two parts, they made their benchmark results look better overall. They saw an improvement on one benchmark, but we ended up swapping which is the fastest of the two approaches. And this will just lead to very non-durable results. And so when I look at something like a comprehension, what I'm going to assess is not, with the micro benchmark, is this faster or slower? I'm going to assess, is this more readable? Is this more understandable? And is this fundamentally faster or slower? And in fact, if the operation I were doing in this comprehension syntax could be written without requiring a function call, maybe it's an arithmetic operation. Here, I could think I don't need a function call. I just need a line of bytecode. Whereas in this formulation, if I needed a function call for that operation, let's do like a square root versus something like this, I might discover a difference in speed as a consequence of the slowness of function calls. And that might be inherent in one of these formulations or the other. Here, we can compare this against another approach using map. And we may discover that this is not really the way we want to write code anymore. But we can see in the Python 3.10 and 3.9 era, that's actually pretty good and pretty fast, even though it really isn't the way we want to write code. And it wouldn't be good advice for us to write our code point in time in this fashion, and then not be aware that this version may have introduced additional optimizations later and is also much more readable. Well, we talked about function calls and the penalty that we pay when we call functions. I want to show you something that I've seen some people do in order to remove or reduce errors in their code. They move imports very, very, very close to where those imports are going to be used to avoid accidentally having an import at the top scope here where, for whatever reason, maybe you no longer need square root anymore, and then this import is still lingering around, and so it's kind of difficult for you to clean up your imports, or maybe there's something that shadows this import and you get into an error with some shadowing. So they'll move those imports really narrowly into the scope where that import is used. I wonder if this is slower than having the import at the top level. Well, we can test the speed of this code just as readily as we can test anything else. And we can see it's 340 nanoseconds per loop. Let's test with the import at the top level. Here, it is 63 nanoseconds per loop. So we might say that there is a performance degradation here, but is that performance degradation really that meaningful? Well, we might say that we don't necessarily want to pay the cost of the initial import, but after that initial import, this should really just be a name binding. It should just be looking up in sys.dot modules what the import is and then binding that name. So I don't see why this inherently should be altogether that slow. But we can see even if we pre-import the module, we still see some slowness here. So that name binding is kind of slow. But what we're missing here is, do we really have functions that just operate on one unit of data that have this kind of narrow scope trick in it? Not really. It's probably the case that we have some function that operates on many elements of data and might use something like this narrow scope trick as part of trying to make that function a little bit, and make that module a little bit easier for somebody to reason about. If we increase the size of the data which this function operates on, we may discover that the performance improvement that we got disappears. 4.6 microseconds versus 4.2 microseconds, not a meaningful difference. It is very often the case that when we look at these micro benchmarks and we compare one against the other, if we are not using realistic data patterns, it is very much the case they might lead us in one direction or the other, where this is just not a very robust performance improvement because it doesn't apply to the actual ways in which we might write our code. This is just noise, just thermal noise and the noise of everything else that happens when you run a Python program. Here's a trick that you'll see in the Python standard library. You'll see it in things like the JSON module, where at some point in time, somebody said a global lookup is slower than a local lookup. In fact, if you look at the bytecode, you might wonder why it is that if I have a function, and that function has a local variable like x here, and a global variable like y here, the name of the lookups are so different. You would think this would be load global, and let's actually do something with x as well. You'd think this would be load local and load global, but this is load global and load fast. You may be aware that when a Python function is executed, all of the local variables are put into a C array called fast locals. And every time you do a local variable lookup, you're actually not doing a dictionary style lookup, you're doing a lookup into a C array. So the reason this is called load fast is looking up local variables is faster than looking up global variables, or at least it was when this bytecode was first named. And so as a consequence, you'll see in the Python standard library some tricks where you'll take global variables and you'll shadow them as local variables. Tricks like this, you'll create a default, you'll have a default argument on this default argument, and here, this will just be the local version. And we could do this with a keyword argument just to avoid somebody accidentally passing this in, whatever the case may be. When we look at the speed of this, we may discover that in older versions of Python, this is materially different than in modern versions of Python, 4.4 microseconds. Let's see what it looks like without that trick in play. 4.2 microseconds, the speed up seems to be very minimal. And so at one point in time, somebody provided that suggestion because something was slow, maybe in the Python 2 era, but it's no longer the case. Think about this. A performance improvement like that was added to the standard library in, for example, the JSON module. Has anybody ever gone back and reassessed if those performance improvements are still performance improvements today? The code in the JSON module has been around for a very long time. Think about the momentum that that code has and the difficulty of changing it now to eliminate that performance improvement and all the validation and testing you might have to do, that doesn't happen to have some other consequence along the way, even though we should think that it should be a mostly innocuous change. Well, you did create an API, you did have arguments that could be passed in, maybe somebody was aware of those and did that, and what should be innocuous will break their code and they'll complain and abuse you on GitHub to say, you broke my example of code that shouldn't be existing in the first place. Whatever the case may be, that momentum means a performance improvement that was added to address a point-in-time issue may then create significant technical debt that you're not even aware of later, because it may end up either no longer being a performance improvement or might even become a performance degradation. There's no guarantee that this global lookup might not have some cache where the presence of the cache might only exist for the global lookup, but might not exist for the local lookup. Whatever the case may be, we have to be very, very careful when we look at these micro benchmarks because they appear to give us guidance and they appear to give us quantifiable, direct guidance. But in every case so far we've seen, there's always something more to the story. Here's something else that we've been told is generally slow, or at least was maybe slow in earlier versions of Python. Looking up a method from a class. So here we have a class, and we're going to repeatedly look up a method, and this method will just be a square root method that'll call our square root function here. And here we can see it takes 8.25 microseconds to call this method, versus if we were to first look up the method and then apply this method as a local variable. So we're going to avoid that dotted access, that get attribute protocol each time. And Here we see 7.9 microseconds, so I believe that was a speed up. How durable of a speed up that is? Well, there are caches for this these days. It may not be a significant speed up here. 8.9 microseconds. Hold on a second. That was 8.9 microseconds. And this was 8.05 microseconds. So this may be lost in the noise of our benchmarking altogether. Here we might try to compare, just in the narrowest case, what it looks like when we have something like a call of a function that's being looked up from a class, some instance method that's being pulled out, and the descriptor protocol and the get attribute protocol in a tight loop. We might see what that looks like, 366 nanoseconds to call a method on a class. And here we might see what happens when we lift this lookup, this get attribute protocol and the descriptor protocol out of the loop. Instead of 366 or so, we see 461. Here, in this case, we can see a slowdown. And so is this advice that we should still be taking? I don't know that it's durable enough advice that we should really be focusing on these micro benchmarks, because I don't think they tell us what we think they tell us. You might say, oh, well, the difference here is that in one case you traded an attribute lookup with the descriptor protocol and the get attr protocol for something using a global lookup, and maybe that's what you're measuring. So here we'll swap it out with a local lookup instead. But I don't think these performance benchmarks measurements are really going to tell us anything that interesting in terms of guiding our use of our code. One thing you might be curious about is this data class. There was an init there, and I haven't written an init in ages. I use data classes every time I want to create a simple holder with maybe one or two methods. Is this data class a performance degradation or not? Well, here we're creating a simple data class and initializing it, and we'll test how fast can we initialize a data class. And we should probably only do this in Python 3, because the data class doesn't exist in previous versions of Python. Here, we can see it takes 271 nanoseconds to initialize our data class. And here, this is initializing just our regular class, 277 nanoseconds. Doesn't seem to be a significant difference in the initialization. For other operations, we may discover that there's a difference here. But unless we have a realistic pattern of behavior, are we really going to be bounded by the initialization of these things? Think about an actual program that you write, especially a program that is very speed sensitive, maybe a program that's doing data analysis. You might have some data classes representing very high-level entities in your code, and you might only create a dozen of these. And if there is a slowdown in the use of something like a data class or something like the attrs third-party library, are you really going to measure it if you only see that slowdown of maybe 50 nanoseconds across 10 instances in your entire program? Or is it going to be the case that the noise of the actual number crunching is going to dwarf the rest of this? It is very commonly the case that people talk about slots as though slots are interesting. They are not. Slots has never been an interesting performance improvement or an interesting memory improvement. In fact, slots is the biggest distraction from what really is a performance improvement in Python, which is the use of restricted computation domains. We won't talk too much about restricted computation domains here, but I want to show you that the use of slots here doesn't really make a difference. It may make a difference on the overall speed of this. Here, you'll see that 250 something nanoseconds against 260 nanoseconds, I don't think we can really measure anything meaningful here. And I think there's really no evidence that slots is that interesting of a thing to talk about compared to the restricted computation domain approach.